Okay, good morning, everybody. Welcome to lecture today. We have a lot to cover today, so I'm going to get going right away, and might be a little fast today, but I want to make sure to get through all the material we have before the exam, which is coming up next week. So any questions before I launch in here this morning? Everything going all right? Okay, well, we got to have a few slides left on our Chapter 9 notes, and then we'll jump into Chapter 10. Hopefully you guys have both of those with you this morning. Remember that here in Chapters 8 and 9, we're focusing on how do we produce data or how do we collect data. We talked about sampling methods in Chapter 8, and now we're talking about experiments in Chapter 9, where we control, we administer treatments to various groups of people, and kind of talking about good ways of doing that. So the last topic we need to cover here in Chapter 9 is that of block designs, and this is sort of a special type of an experimental design. And the thing that's different about these designs is that we use this notion of a block, which there in the first bullet point is our definition. We're going to say a block is a group of individuals that are known before the experiment starts to be similar in some way. So this is another element of control that we're introducing into our experiment, is that there's something about the people that we're studying or individuals that we're studying that we know, and we can put them into blocks. And so then in a block design, we randomly assign the people in each block to get our treatments. So each block will have all of the different treatments that we had discussed previously. And I'll show you an example of this, but for now, just keep these definitions in mind. That I'm creating groups before I randomize people. It's kind of the main idea here. And then, kind of even going one step further, another sort of subset of block designs is this idea of a matched pairs design. And so again, on the previous slide, I said that a block I was sort of putting people into groups based on something that I knew about them. So here my groups are going to consist of pairs of subjects that are closely matched, so that they're similar in some way. And then I randomly assign my treatment to each person in my pair. Or a variation of this could be when I use one subject and give them both treatments. So again, if we're trying to get at, if we're trying to find pairs of subjects that are closely matched, the person who's most similar to you is yourself. So if we can give you both treatments, then that's kind of the best case scenario. So just using one subject and giving them multiple treatments, but that's not always possible or practical, is the note that I'll make there. And the example that I would say is that what if my treatments are surgery or some sort of pill or other drug? If I give people in my study, if I give them both surgery and then later some sort of a pill or a drug, I can't really separate what's making the difference. So if you're one of the subjects who gets surgery first and then later you get some sort of a drug or a pill, how do I know which one of those things actually made you better? So anyway, matched pairs, kind of the ideal situation is when I can give the same treatment to both treatments to the same person, but there is another variation where we can try to match people who are similar. And kind of like I was saying, block designs, so either a block design or a matched pair as well, is another form of control in an experiment. So again, we talked a little bit about confounding variables and the effect that they might have, kind of those lurking variables. Doing a block design is another way that I can control for that. So I can bring those confounding variables into the experiment and kind of control for them. So for example, if we go back to our Crohn's disease study, remember we were giving our subjects either some combination of a pill and an injection or a placebo. So there was some combination there, if you remember back to the first example. But how about suppose that now the researchers believe that a subject's response to either the injection or the pill might change based on how old they are. So again, kind of thinking about that's so here in this case, age would be a confounding variable. Because if I don't, again, if I get results at the end, maybe I had all my older folks in one group and my younger folks in another group. Maybe that's how the random assignment panned out, and so the age might have had some effect that we didn't control for. But what we can do here is we can use age then as our blocking factor. So we can block by age to minimize the variability that we get in our results. So let me quickly draw out a diagram for what this might look like. It's going to be a variation of what we saw earlier. So suppose we have two age groups. Let's say less than 35 and greater than 30, greater than or equal to 35. So suppose I have two age groups here that I want to consider. So maybe that's kind of the age at which I know there's some effect going on for these injections. So then I can take all my subjects, I can split them into my two age groups, age group 1, age group 2, and I think if you go back to your notes, we had 3 treatment groups, or was it 4 maybe? We just had 3 treatment groups. So I've split my people into age groups, and let me make a note here. This is done non-randomly. Right? So whatever your age is, that determines what group you go in, not some sort of a random assignment. So I split my people into groups based on something I know about them, and then I kind of go with what we did before. So now I split each one of these groups into my 3 treatments. So treatment 1, treatment 2, treatment 2, treatment 3. And then I can kind of come back and compare my results. And one other note that I'll make here is once I've split my people into age groups, then I kind of do as usual. And so in this, sorry, there's a lot of. So in this step here, this is going to be my random assignment. So again, the difference in a block design is that that the first step is that I put people into groups based on something I know about them. So that's made a note that that's a non-random assignment based on whatever your age is determines what group you get in. And then after that, I put you into groups. And then I give you a treatment randomly. So for my age group 1, I randomly assign all the people in those to one of 3 treatments. Same for the other group. So there's just a slight variation on that first step in which I'm splitting people into groups. Any questions on what I'm talking about here? Or okay, and then a quick example here of a matched pairs experiment. So sorry for the University of Florida example here. I'm not the biggest fan of Florida. Maybe Dr. Baker is. I don't know. Anyway, at University of Florida, scientists wanted to assess the effectiveness of a new Kool-Aid beverage on his athletes, maybe. How might he administer a matched pairs experiment? So let's suppose my treatments is the new Kool-Aid beverage. Maybe my treatment 2, excuse me, it's a placebo or something. And so suppose my subjects are maybe 100 football players. So So how could I do a matched pairs experiment here in this case? I guess first of all, is it possible to give both? So again, remember the matched pairs is kind of my ideal setting is that I can give both treatments to the same person, and then if not, I try to match people up that are similar. Can I give both treatments to the same person here? Why do you say no?
Because if you give them the placebo and that, you wouldn't know if it's helping or not.
Okay, so if I give them both the placebo and the Kool-Aid beverage, I won't know which one is helping them. That is correct, but yeah.
Could you also like to use the placebo on one game and then you thing in a different game so you could compare the effects that it has on a particular game?
Absolutely, yeah. So we can bring time into this equation, right? So the response was we could give the Kool-Aid or I could use the Kool-Aid for one of my games for 1 week's game, and then the next week maybe use the placebo. So sort of conceptually, if I drink placebo one day and then I drink the Kool-Aid maybe a week later, there's not really going to be a crossover effect there. It's kind of the main idea. So you're right. If I tried to do that on the same day, that would be bad. But if I spaced it out over time, that would work. So I could randomly split the players into two groups. In 1 week's game, half the people get the placebo, half get the Kool-Aid, and next week vice versa. So again, I can randomly assign week 1 who gets the placebo, who gets the Kool-Aid, and in the following week I can just keep the same groups and switch those people around. So that's at least one way to set up a matched pairs. If we could do it the other way as well, where we try to match people up who have some sort of similar characteristics, and then do this all in 1 week. So if you have a short amount of time or something, that would be an alternative. But yes, this is one way of setting up a matched pairs experiment. Mm-hmm. Oh, okay. Just stretching. Alrighty. Any questions you guys can think of on matched pairs or block designs or anything like this? Yeah. Oh yeah, definitely. Just gets worse for a little bit. Yeah, no problem. Make it nice and dark in here. Yeah.
If you're trying to draw up a little flow chart for the design and you're doing it two different groups for the same people, how would that look?
Yeah, so if I was trying to diagram this kind of a thing, that's a good question. You'd have to get creative. But I mean, keeping in mind here that I think the most important thing to keep in mind is that so I randomly split my people into groups of 50 into two groups, and then I would want to keep those same groups for the next week, right? So I've randomly assigned who gets the Kool-Aid, who gets the placebo in the first week, and since I want each person to have both things, I need to switch those groups for the second week. So I mean, it could look kind of like this kind of a thing. But if you can take it down a little lower for you. If you could somehow denote that you have time as a factor in there, that would be, yeah. Good question. Now it's really dark in here. Yeah.
For that, could you just kind of make two, I know it's kind of weird, but two in a row. So you could just extend it and say other treatment given and then compare them again.
Yeah. Definitely, yeah. So you could kind of split people into two groups. Week 1 would be the first set, and then you could maybe draw another line to week 2. That would be a good way to do it for sure. I don't think you'll be expected to diagram a matched pairs experiment, but it's good to think about what you would do if you were expected to do so. Okay, well, that brings us to the end of chapter 9 here. And sorry to kind of rush through this, but we have a lot to get through in chapter 10 here today as well. So if you have your chapter notes, 10 notes, you can kind of flip over to those. And now we're going to be discussing probability, which I think is really interesting, but it can be tricky. So let's take a look at what we're going to be doing here. So kind of big scale idea of what we're doing here is that the theory of probability allows us to go from data collection, so what we just talked about, to inference. So this word is an important word. We talked about this in chapter 8. Inference is where I'm using the results from a sample that I take to infer something or to make a statement about the larger population. So again, kind of remember our overall goal is if I'm taking a survey or something, right? I want to use what I get from that survey to say something about the bigger population. So maybe I take a random sample of students at Ohio State to say something about the larger student body, or maybe I take a random sample of Columbus residents and say something about the entire city of Columbus. And so probability is kind of what allows us to go from collecting data to making a statement or doing inference. So thinking back to, well, I think this is actually chapter 8 that we talked about this. And I switched this up in your notes since we used a different example. But we talked about doing a stratified random sample where I had 250 students and 50 faculty members. So suppose that I'm focusing on my faculty members now. Suppose that I take a simple random sample of 50 faculty members, and maybe one of you guys or all of you each take your own simple random sample of 50 faculty members. So my question is, will they be the same? If I take a random sample of 50 people and you take a random sample, are those going to be the same sample? So will they have the same people? And of course not, right? So this is kind of like when we were doing this by hand. Whatever row of the table you picked, whatever the table random digits row that you picked to start in, kind of determine what your sample was. So you won't get the same simple random sample, and the idea that but that this is not a problem. And that's kind of what I was saying. We can use the rules of probability to kind of still make a generalization to the population. So this is a very, very important idea, is that that samples vary. So you take a sample, you're going to get one result. I take a sample, I'm going to get another result. And we want to kind of address how we're going to deal with that situation. So because of this randomness that will happen in our groups, other things about our sample might differ. Maybe they'll have a different average age, or maybe they'll have a different opinion on whatever issue that I'm asking about. And then just again a note that it's not going to be a problem. We're going to kind of look at how to address dealing with this issue. Okay, so the basic idea of probability here, and this should be back on track with your notes, is that, and so kind of why we want random sampling and why we talked about randomized comparative experiments, which is just where we randomize who gets what treatment. The idea is that it is because we have this chance behavior going on, the impersonal chance that we talked about before, which is unpredictable in the short run, but has a regular and predictable pattern in the long run. So let's take a look at a quick example of what I mean by this, and we'll do this very quickly. So if you look at the row that you're sitting in, and count up how many women are in your row, how many men are in your row, and then the total number of people in your row. So I'm going to pretend I'm in the front row. So I have 3 women, and if I count myself, I have 3 men, and I have 6 total students. So in my row, and you can write out what this is in your row, I have 3 out of 6, or 0.5. So that worked out a little too perfectly. What do some of the other guys have as proportion of women?
5, 6.
5 out of 6? 2 out of 2. Okay, we got 100%. 2 out of 2. Who else has a result for me? Someone from the back? I could. 3 of 4. Thank you. So the point is that in each row, kind of thinking about that, it's not a random sample, but each row is going to have a different proportion of women in that row. And again, we have 6 people in a row, 4 people in a row, 5 people in a row, whatever. What would happen if each row you guys had 200 people in it, and then we counted up the proportion of women that were in that row? Or what about 2,000 or 20,000? What proportion would you expect of women to be in your row as these numbers got bigger and bigger? Did I hear something? Yeah.
Just get closer to 1 over 2.
Yeah, exactly. It'll get closer to 1 over 2 or 50%. Because that's again, that's not going to be exact, but again, sort of the population of people is kind of 50-50 male female. So exactly, as your samples get bigger, you would expect that you'll get closer and closer to an overall number of 50% there. And so this is what I mean by going back 2 slides here. So kind of thinking about the proportion of women in your row is kind of a random thing, right? So in just your own particular rows, when there's 2, 3, 4, 5, 6 people, it's sort of unpredictable what the proportion of women will be in your row. But then in the long run, so as my sample gets bigger and bigger, I sort of have a predictable pattern going on there. So about 50% of women will be 50% of the people would be women. So that's what I mean by unpredictable in the short term, but predictable in the long term, or sort of as your sample gets bigger. So this leads us to more formal definitions of the term random that we've been using a lot in this class. So we call a phenomenon random if, again, individual outcomes are uncertain. So that's kind of think about the short term. We have sort of unpredictability going on there. But nonetheless, we have sort of irregular distributions of outcomes in a long run of repetitions. So as again, kind of with the previous example, as my sample gets bigger and bigger, as I include more and more people, I would kind of have more of a predictable result. So that's what I mean by a random phenomenon. And then this leads me to the idea of what probability is. So the probability of any particular outcome of a random phenomenon is the proportion of times that outcome would occur in a very long series of repetitions. So again, very long series of repetitions, again, kind of thinking about as my sample gets bigger and bigger, the probability, the proportion of women in that group will approach 50%. Proportion of males will do the same. That's what I mean by random, and that's kind of the probability is kind of like the likelihood of an event happening. And so and this leads us to the idea of a probability model. And so once we know what a probability model is, we can kind of start to work with the probabilities in a particular example. So there's 2 things here that are involved in a probability model. It's kind of like a marginal distribution here. You think about it that way. It's kind of a motivating example. Is that we list out what outcomes can occur, and then secondly, how often we expect those values to occur. So again, when you're asked to write down or think about what the probability model is, here's what we need. We need what outcomes can occur and how often we would expect those values to occur. So more definitions here. The sample space, so whatever a random phenomenon is, the sample space of that is going to be, the first part of what was on that previous slide is the set of all possible outcomes. And we'll take a look at an example here and show you what all these things are. And then an event, what we're going to call an event, is an outcome or a set of outcomes of a random phenomenon. So it's going to be individual things from our sample space, or maybe combinations of those things. And then our notation, which we're going to use a lot here, this is going to be our notation. We're going to use a capital P, and then put an A inside the parentheses. And so for an event A, so A can be a generic event. We'll talk more about that. We say this: the probability this is the probability of A. So whenever you see P parentheses with something inside of it, probability of, and then A, whatever that event A might be. Okay, so let's take a look at a simple example to maybe kind of show you what I mean. Okay, that was already on there, I guess. So here's my example. I don't know if we have any people in genetics in here, or maybe you remember this from your high school courses. But a Punnett square is something we use in genetics and that's often represented as a two-way table. So for a certain characteristic, for thinking about what the children will have, you think about the genetic makeup of the mother versus the genetic makeup of the father, and that's what we have here. So this is the mother, and this is the father, and then the children will be inside this other square. And so we're looking at hair types here. We're going to have two possible hair types for the father and mother. We have C, which is going to be curly hair, S is going to be straight hair, and then wavy hair is going to be sort of the combination of those two things. So again, keeping in mind that I want to focus on kind of what the children have going on here. That's kind of the main part of this table. Let's think about what my sample space is for the children's hair types. So what I'm going to do is I'm going to put a capital S. That's going to denote my sample space. And then I can put it in curly brackets. I have three possible hair types. So I have curly, which is CC. I have straight, which is SS, and I have wavy. So again, that is curly, straight, and wavy. And of course, there are more hair types than just those three, but let's pretend we're in a very simple case here. So this is my sample. This is, again, kind of in this example, we're assuming this is the only possible outcomes that we can get for parents that have either curly or straight hair. So that's my sample space. An example of an event in here would be, so for example, it could be any one of those things in my sample space. So maybe the event that I'm interested in is curly hair, or straight hair, or of course wavy hair would be an event too. Put one. I could also, again, remember, an event can also be combinations of outcomes. So those are just single outcomes, but the event could be also curly or wavy hair. So I could do things like that too. And there's many more. There's many other. Well, not many, but there's other events that are in this sample space that I haven't written out everything, but just some examples of what I mean by an event. How can it be curly or wavy hair? So just again remembering that an event is any one particular outcome, or it could also be a set of outcomes. So yeah. So I guess I can't have curly and wavy hair, but I could consider, what if I want curly or wavy hair? Yes. Good question. So those are just some examples of what events are. And finally, then I can write out what my probability model is that will allow us to answer some of these questions. So again, I need two things. I need one. I need to list out what the sample space is, what the possible outcomes are, and then the probability of each of those outcomes. So again, the hair type possibilities that I have are curly, wavy, and straight. Sorry about that. And then remember this P with parentheses of hair type, this would be the probability of each hair type. So again, looking up here at the little Punnett square that I have here, what's the probability that the child will have curly hair? 25%, right? So I have 1 out of 4, or 20, or 0.25. And we'll kind of actually, so now in this chapter we'll go more with the decimal representation. So we'll think about the proportion instead of the percentage. So again, 0.25 is 25%, but let's start writing just 0.25 there. So very good. So wavy, then what about wavy? What's the probability of a child having wavy hair? 2 out of 4, right? So, or 0.5. And then finally, the probability of having straight hair, then 1/4, exactly. So there it is. Very, very simple. There's the probability model for this example. So I've listed out what the possible outcomes are, as well as what those probabilities of each of those things are. And yes, so we have 3 outcomes here, but they're not all equally likely. That's an important note. Not all equally likely. Sometimes your outcomes will be equally likely. Here, turns out that they are not. So this leads us, we can think a little bit more about types of probability models that we have. The first type is this thing called a discrete probability model. And this has countable outcomes, which simply means that I can count them. So if any of you guys took any higher level math classes in undergrad, well, I won't get into any of the details there, but if countable is a familiar word, then maybe this scares you, but don't worry about it too much. So what I mean by that is that the outcomes assume fixed values or are some sort of number going on there. And then to assign probabilities in the finite or the discrete case, I can do just what I did before, is list all my outcomes and then list the probabilities for those individual outcomes. So I'm going to skip over Dr. Baker's example and use my own. So an example here is suppose the sort of the random phenomena that I'm interested in here, the random phenomena. Not that I have anything against his example, but it didn't quite feel like me. So the random phenomena I'm interested in is the number of times in a game that Kenny Guyton will either pass the ball or throw the ball. And I hope I spelled his last name there right. I might not have. Is that okay? Did I butcher it? So why is this a discrete probability model? Yes, so I can count. Yes, exactly. So I can count how many times he passes or how many times he throws the ball. But yes, so that is correct. But the thing that I need to be able to count is the number of possible outcomes. So you're correct. I can count up the number of times he throws or passes, but it's discrete because the possible. So the possible outcomes here are passing or throwing. So my sample space is going to be on each play he either passes or he throws. So again, yes, I can count the number of times that he does that. That's what I'm interested in doing. But think about each play is kind of, we're considering each play individually. The possible outcomes from that is that he can either pass or throw the ball. I guess he could also run the ball, but and now I'm realizing that is the same thing, isn't it? You guys gotta call me out on this. So this should say run. How embarrassing. Passing or oh my goodness. It's been a long week, you know what I mean? You guys gotta speak up. I was testing you and you all failed there, right? So anyway, when I'm talking about a discrete probability model, I simply mean that the outcomes, I can count how many outcomes I have. So there's a kind of distinction going on there. Okay, so that's one type of a probability model that I have. Oh, I'm going to give you a few other examples here. Sticking with this discrete probability model. So again, the children's hair color example. Why is this a discrete probability model? Same kind of a question. Yeah, I can count the hair types, right? Or I can list them out. So again, my sample space was curly, wavy, or straight. And then again in my probability model, I listed out my individual probabilities. But there's a few other types of questions that I can ask here, such as what is the probability that the child will have straight or wavy hair? So in my notation, this is going to be the probability that the child has straight or wavy hair. What is that going to be? If you look back at the probability model we wrote out. Yeah. Yeah. Say again? 50%. Okay, so if we have straight or wavy, so I want to include 75%. All right, yeah, so I want to include, what is this, straight or, if I want to include both of those groups, yeah, this is going to be 0.5 plus 0.25 equals 3/4 or 0.75. So we can note that this is equal to the probability of straight hair plus the probability of wavy hair. So this is kind of connecting back to chapter 6, our two-way tables. We were asking those and questions and the or questions. It's kind of an extension of that. So the probability of straight or wavy is equal to the probability of straight hair plus the probability of wavy hair. Another question we can ask then is, what is the probability that the child will not have curly hair? So again, my notation, I'm going to write out probability of not having curly hair. Who can help me out there? Same thing, 0.75? Because that's actually the same exact question that we just asked, right? So not having curly hair means that I do have straight or wavy hair. But another way of doing this would be 1 minus the probability that I do have curly hair. So that's again 1 minus 0.25. So again, there's a couple ways you could get to that number, but Okay, very good. So, boy, running low on time here. So again, we have discrete probability models where we can count the number of outcomes that we have, or we can list them out in a sample space. The other type of probability model we have is that of a continuous probability model. So, kind of get you thinking about what this is. Consider I have two situations here. The first one is the number of vehicles that are owned by a household of 5 students. It's my first situation. The second one is the actual amount of gas in a vehicle that has a 20-gallon tank. So what is the difference between the sample spaces? Well, let's first write them out. So the sample space for the first one, what are the possible number of vehicles that I could have owned by a household of five people?
0, 1, 2, 3, 4, 5.
Yes, exactly. So either those 5 people could have 0, they could all together have 1. And I guess we can maybe just assume that everyone only has 1 car, right? So it could be more than that, I guess, but we're just going to pretend that those are our only choices. What about the sample space for my second example? What's the possible numbers for the amount of gas that I have in my car? That's 20. Yeah? 0 to 20. So any number between 0 and 20? Yeah, exactly. So this is any number between 0 and 20. So this would be things like 0.1, I could have 19, 13.6, I could have 3 times the square root of 2, I could have lots of things like that. So whatever, I could have any number between 0 and 20 for the amount of gas that I have in my car. So it's not just 0, 1, 2, 3 up to 20. And so the key down here is that I can't list all the possibilities for S2. So in my second case, I cannot list out all the possible amounts of gas that I might have in my gas tank. And so that leads us to the idea of this continuous probability model. And so for the second example, we're going to return to that idea of density curves that we discussed in an earlier chapter. I think it was back in chapter 3. So if you remember, a density curve describes some overall pattern of a distribution, right? So when we're looking at histograms, we often drew a smooth curve, and that was kind of what we thought about as a density curve. And it had these two properties: the area under the curve. So remember, we had that correspondence between area and proportion, probability, kind of. If you can think about that now. And then we had the density curve was always above 0 or at or above 0, and had an area of exactly 1 underneath it. So kind of think about the normal distribution here. That's kind of our classic example of a density curve. If we wanted the proportion of observations that fell between some range, then we found the area that was under the curve between that range. Kind of that's the idea that we're working with again here. And so this is so there's kind of the density curve and a continuous probability model is kind of the same thing. So it assigns probabilities. Again, we can't list out all of the possibilities that we have like we did before, and so we therefore also cannot list out the probabilities for all of our events happening. So instead, we'll use the idea of a density curve to describe these things, and then keeping in mind that area is going to correspond with probability, so or proportion is going to correspond to area. Okay, so an example that I guess we didn't cover this, and we had a different set of Chapter 3 notes. But an example that we could look at is, so if we have a student, Sean, who the number of minutes that he arrives before class is uniformly distributed between 5 and 15 minutes. So if I draw my density curve, this is kind of like that bike trail example that we looked at. If x down here equals the how many minutes before class Sean arrives, we're going to assume it goes between 5 and 15. and then is uniformly distributed. It's supposed to be a straight line. So it's uniformly distributed. It's kind of that flat line. So again, even though it's not a curved line, this is a density curve, and this is going to represent the probability model for this continuous case. So then, give you a little quick quiz here. What is the height of that rectangle? What did you say? So remember, the area under my density curve has to add up to 1. So if I want the area under that the area of that square to be 1, what's the height of that rectangle? 0.1, exactly. So again, I have, this is 10. 15 minus 5 is 10. So I have 1/10, or 0.1 is my height there. And then we can answer a few questions. What proportion of the time will Sean arrive between 7 and 10 minutes? So let me sketch this out again real quick. Here's x. Here's 0.1. The density curve. So I want the proportion of times that Sean will arrive between 7 and 10. So there's 10. Let's say here's 7. So again, if I want the proportion of time, so if I want the probability, I can think about, remember, the area. So if I want this area in there will tell me about the proportion of times that he arrives between 7 and 10. So probability that Sean is 7 to 10 minutes early is simply the area of that shaded in, simply equals the area of that shaded in spot, which is, again, the height of that is 0.1, and then I'm going to multiply that by times the width, which is 10 minus 7, or 0.1 times 3, 0.3. So again, the probability that Sean arrives between 7 and 10 minutes early is 0.3. 30% of the time he will arrive that much early. Another question, what is the probability that x is at most 7 minutes? So let me again draw my picture here. It goes from 5 to 10, 15. There's x. Remember, x is the number of minutes. Drawing my curve here. So here is 7 minutes. And then which area do I want to shade in under that curve? I want the probability that x is at most 7 minutes. To the left, right. So probability that x is at most means it's 7 or less. Exactly right. So again, the probability that Sean is at most 7 minutes early. I'm kind of thinking about what our notation is. I can simplify this a little bit. Again, x is the number of minutes that he's going to be early, so I want the probability that x is less than or equal to 7. It's kind of just using the fact that I'm denoting x as the number of minutes early that he is. So again, that's going to be the shaded area that we have here, which the area of that is 0.1 times 7 minus 5. Equals 0.2. So is everyone okay with what I did there? I wrote out the probability of Sean being 7 minutes, at most 7 minutes early. Is everyone okay for me going from that to probability of x being less than or equal to 7? And we're going to see why that's the same thing. So again, our notation is just going to allow us to write things out a little in sort of shortened form. So I'm going to start doing this more as we go forward here. Okay, and the last example here, what is the probability that X is exactly 7 minutes? So the probability that Sean is exactly 7 minutes late. Here is 7. And so I want the probability that Sean is exactly 7 minutes early. So kind of my shorthand again here is probably that the number of minutes that Sean is early is exactly equal to 7. Well, again, we want to find the area under the curve that's actually equal to 7. So what's the area? Again, I can take my height, which is 0.1, and then the sort of the width of that space is it goes from 7 to 7. This is actually 0.1 times 0 equals 0. So that's a strange result, I think. The probability that he's exactly 7 minutes early is equal to 0. And that would be the same for any other number that I picked out in there between 5 and 15. So again, is it possible that he would arrive exactly 7 minutes before class? Yes, it's possible, right? He could be exactly 7 minutes early. But what we have here is that the probability of that happening is 0. That's a little bit of a paradox, I think, but that is true. Okay, so just a few more definitions here for you. And I have 3 minutes, so this is going to be very quick. But a random variable is a phenomenon whose value is a numerical outcome of a random phenomenon. So remember, the random phenomenon is something that we're talking about in general that is something that has an unpredictable short-term behavior, but sort of long-term has this pattern that we can talk about. And a random variable is just simply a variable whose value is a random phenomenon. And so then, just kind of rephrasing what all these things are, the probability distribution, that's kind of like our probability model. So probability distribution, or it's the same as the probability model. It tells us what values that random phenomenon can take on. So again, like what number of cars that our 5 students have, or how much gas is in my tank. And then the probability distribution tells us how to assign probabilities to those things. So we can either list out our possible outcomes, and we can then figure out what the probabilities are, or we'll use the idea of a density curve to kind of show how the probabilities are distributed there. And then these variables can be discrete or continuous. That's kind of what we've just been looking at. We can have either the number of cars that the 5 students have, which is discrete, we can count out how many of those are, or continuous, like the amount of gas in the tank, or the minutes that he arrives early to class. And finally, this is kind of formalizing the 2 questions we did about the hair types earlier. So this was like the probability of curly, or what did we do? I guess we did straight or wavy. Keep that in mind. That was kind of like what we did there. And if those events can't happen at the same time, then we can add them together. That's what we're going to call our addition rule. So the probability of one event happening or another event happening is simply you can add up the probabilities of each of those events happening. And then the complement rule. This is kind of like the probability of not having curly hair. So the probability that some event does not occur simply is equal to 1, because that's the probability of everything, 100%. And then I'm subtracting off the probability that it does occur. So again, the probability of not having curly hair was equal to 1 minus the probability of having curly hair. So I did have a quick question that came in on here. Let me jump back to, oh no. Well, I guess we're done. Someone said, why isn't the probability for Sean being exactly 7 minutes early 1/10? And that would be because if we're calculating the area under the curve that corresponds to the range of values that we want. And the range of values is just one number. So the range goes from 7 to 7. And so the width of that range is 0. So again, we're taking the area of just a line, which is 0. Sorry that was so fast, guys. But again, the recording will be up to check back through any of these things if I went too fast. Have a great weekend, and we'll see you guys at the exam on Tuesday. Happy studying.
Complete notes on Harmon.
Uh,
Shoot up to chapter 4. I wasn't sure if you were having any of the other ones on.
No.
Okay.
I will not be putting it together. Check the videos, though, if you need to go back and fill some of that stuff in. If you could send that to your TA, that would be good. Or did you, so your recitation was yesterday?
Yeah.
Okay. So just bring that to the exam on Tuesday. If you didn't turn it in yesterday, you'll get the same extra credit.
Really?
Handed it on Tuesday.